Hello everyone and welcome to Pat Problems with Helena and Kat. My name is Kat, I'm the Physics Access Officer at Oxford University, and today I'm going to be talking you through the solution, or my solution rather, to question 2 from the 2016 paper. Now I say my solution because with the PAT there are always lots of different ways to work through problems, just as in real physics. This problem is a maths problem from towards the start of the paper, and it asks you to find all of the values between 0 and 2 pi of theta for the equation root 3 tan squared theta minus 2 tan theta minus root 3 is equal to 0. And we're told that this is a 5-mark question, so straight away we know there's going to be quite a lot to this. This problem, I'm going to try and break it down in a couple of steps. And the first of those steps is recognising that this is a quadratic equation. So what I'd like to do to make my life a little bit easier is start out by dividing everything by root 3. And that straight away is going to give me a slightly different looking equation, which is tan squared theta minus 2 over root 3 tan theta minus root 3 over root 3, which is just minus 1, which is equal to 0. Once I'm there, I have got a quadratic equation where the variable is tan theta. Therefore, I can use the quadratic formula, where usually we've got x, and our solutions are minus b plus or minus the square root of b squared minus 4ac, where a, b, and c are the coefficients of that quadratic equation. I'm going to work through not solving for x, but solving for tan theta. So my b, which is my coefficient of the tan theta term, is minus 2 over root 3. So my first pass through this, I'm going to put in as many brackets as I need to keep myself happy. So this is minus b plus or minus the square root of b squared, again, all the brackets, minus 4 times a, which is just 1, times c, which is negative 1, all over 2a. And although 2 times 1 is pretty clearly just 2, I'm going to leave it in just so that I can see when I go back to my own working what I've done. And now let's start simplifying. So I've got tan theta is 2 over root 3 plus or minus the square root of. Now minus 2 over root 3 times minus 2 over root 3 is going to give me positive 4 over 3 plus 4 inside that bracket, and that is all over 2. Keep simplifying. I'm going to get tan theta. Now that 2 over root 3 all over 2, what I'm going to do is I'm going to bring the half out to the front. And this is something that you see quite often solving longer quadratics, is bringing that factor of 1 over a from minus b squared over 4ac all over 2a. So 1 over 2a comes out to the front to make the rest of your calculations easier to read. There's not really any other reason, but it puts it in a much simpler format for doing this bit. And then 4 over 3 plus 4, well, put that into thirds, I'm going to get 12, 16 over 3, so plus or minus the square root of 16 over 3 in brackets. So far, so good. So I'm getting there actually. I've got now half times 2 over root 3, so I've got 1 over root 3 is my factor before the plus or minus. Just shuffle up so we can keep seeing there. And I've got a half times the square root of 16 over 3. Careful you don't lose the square root and accidentally just take it up to the top. It's still the square root of both terms. So my solutions for tan theta are looking like 1 over root 3 plus or minus the square root of. Now, root 16 is 4. 4 over root 3 all over 2 plus or minus 2 over root 3. What I then need to do, just as with other quadratics, is separate out those two solutions and actually explicitly deal with my two options. I'm going to take my space. I'm going to say tan theta is either equal to 1 over root 3 plus 2 over root 3, or tan theta is equal to 1 over root 3 minus 2 over root 3. So this solution is 3 over root 3. And if I rationalise that by multiplying the top and the bottom of my fraction by root 3, I'll get 3 root 3 over root 3, root 3, which is 3 root 3 over 3, which is just root 3. So that's my first option for tan theta. My second option for tan theta is just negative 1 over root 3. So I have now got two solutions for tan theta. One which is positive and one which is negative. I'm going to be thinking about in my graphs what that might look like, just because that's the way my brain works. I tend to do most of these things graphically. I've recognised the quadratic. I've used the quadratic formula. My next step is to spot that these are exact values. And this is very much something, just the more you do, the more you spot. And you might well know that exact values are that tan of pi by 6 is 1 over root 3 and tan of pi by 3 is root 3. If you don't know those off by heart, pick a single value in either degrees or radians to memorize and learn how to construct the triangles. So I'm just going to take a little detour of the two triangles which you need to do your exact values. You need one which is 30 or pi by 6 and 60 or pi by 3, and you need one which is 45 and 45 or pi by 4 and pi by 4. This one is going to be 1 and 1, giving you a hypotenuse of root 2. And this one, I always remember that sine of 30 or sine of pi by 6, which is opposite over hypotenuse, is a half, giving me this one is root 3. And then I can use SOHCAHTOA. The tan of pi by 6 is the opposite over the adjacent, so tan of pi by 6 is 1 over root 3. Tan of pi by 3 is opposite over adjacent, which is root 3. So they are the opposite angles in that 30, 60, 90 triangle. That's just a detour to remind you for the sake of completion. Okay, we have now got what I tend to refer to as reference angles. We have a couple of solutions which are correct. So for tan theta is root 3, I absolutely get a solution which is root 3. Sorry, which is pi by 3. I'm good to go. But there are other solutions as well, and so I need to consider each of these individually. And there are two different ways to do this. You can either do it using cast diagrams or graphically. So I'm going to start by doing it with a cast diagram method, which is where I have this quick mnemonic which runs anti-clockwise from 0 all the way to 2 pi and lets me know in which quadrants each of my trig functions are positive. So if I want tan to be positive, I get a solution between 0 and pi by 2 of theta, which is this reference angle, pi by 3. But I also get a value down here, which is pi plus my reference angle, or pi plus pi by 3, which is 4 pi by 3. So I get two solutions of this. If we think about this graphically, I'm going to do a quick sketch of the tan graph, which, as you know, is the trickiest one to do a quick sketch of. But tan is positive in the first quadrant, it is negative in the second quadrant, positive in the third quadrant, I didn't quite go far enough along, and then negative again in the fourth quadrant. So when I am looking for tan of theta to equal root 3, or about 1.4, I'm going to get this first value, which is my pi by 3, and I am also going to get this second value, which is pi plus pi by 3, because on this graph I have got pi as my center point of my graph, 2 pi as the end, and here I am in radians. So here are my two solutions. I'm going to highlight that with a pretty colour because I can. So that is the pi by 3 solution. That is the 4 pi by 3 solution. And I figured it out with the cast diagram, but I could also have done it graphically. Let's do our next one. Tan of theta is negative 1 over root 3. Now this one, my cast diagram is a little bit different because I don't want tan to be positive. I want tan to be negative. So I know I'm going to get a solution in the second and the fourth quadrants. So at no point is my reference angle of pi by 6 actually a solution. Instead, I'm going to have pi minus my reference angle. So theta is pi minus pi by 6 radians. And I'm going to have theta is 2 pi minus the reference angle. And that gives me 5 pi by 6 and 11 pi by 6 as alternate answers. For the sake of completeness, let's have a look on the graph again. I'm going to do it with the same graph. So negative 1 over root 3. Let's say it's about here. I have no solutions in the first quadrant. I have a solution in the second quadrant. And I have a solution in the fourth quadrant. Symmetrically, that is my reference angle there. I'm going to highlight that. That is my reference angle there, my pi by 6. And my symmetry tells me that I am looking at that distance and that distance. So my solutions for this overall, to go back and answer the question, are theta is equal to, let's see if I can do these in order of size. I have pi by 3, 5 pi by 6, 4 pi by 3, and 11 pi by 6. That is my solution to question 2 of the 2016 paper. It is worth noting that in 2025, which is the year I'm recording this in, our PAT is going to be multiple choice. It will not affect the type of questions that we ask. There will simply be a final extra step where you are asked to select appropriate solutions from your list. And you can easily imagine that your incorrect answers are going to be things like not noting which quadrants your answers are in. So getting mixed up and saying that pi by 6 is a solution, for example. So none of the answers that you encounter in the multiple choice are obviously and deliberately wrong. There are no answers to throw you. All of our answers are plausible and will come from simple mistakes to make. So for example, the other answers may be based on an incorrect rearranging up here, on incorrect reference angles down here, or even on taking your incorrect exact values. I hope that helps, and I hope the little detour I took into exact values and cast diagrams versus graphs was useful as well. I will be back for our next solution video where I'm going to look at question 5 from the 2016 paper. Thank you very much. Have a lovely day, everyone.